a bunch of announcements before I begin. First, the homework is due in the afternoon in class. So you should have received an email from me regarding how the homework should be submitted. If you didn't, send me an email as soon as possible. It means that you're not on Courseworks. And by now you should have been on Courseworks. We're going to get all the handwritten documents submitted in class, and anything electronic has to be dropped off in the grader's Dropbox. And the instructions were in the email about how to do it. If you, every year I find some people who want to type out their solutions. In case you do and you don't want to print it out, you can just drop off the entire solution into the TA's Dropbox. The first exam in the course will be next Thursday in the second session. The thing in Courseworks actually says July 22nd, Thursday. The date and the day are inconsistent with each other. It's July 21st, Thursday. In the second session, the exam will be for 2 hours. And I think we'll start on quadratic programming on Tuesday, but that would not be included in the exam. The midterm will be only on linear programming. And between the two classes, between now and the afternoon class, I'll send out a detailed email exactly telling you what are the various things you're responsible for. Just as a sort of a starter, you're not responsible for actually computing things with simplex. You don't need to know anything about Tableau, dictionary, whatever it is, that elementary row operations, column operations, nothing of the sort. What you are responsible for is, if I give you a small LP to say whether a particular corner is optimum or not, how do you just check that? You will never be asked to solve an LP. You will be asked to interpret solutions. Okay, and I will give a more detailed description. All right, so before I begin today's lecture, any questions from last time? Anything that you didn't understand? So after class, people mentioned that I drop terms which are financial in nature, which many of you may not understand. So if I do that, just stop me and I'll explain it to you. I don't want it to sound as if I'm trying to drop words which I don't want to explain. It's just that sometimes I just assume that all of you know exactly the same thing that I do, in which case you shouldn't be here in this class. But anyhow, so if you just stop me and I'll explain any term. Most of the terms are completely simple, but something that you may not have seen. Any other questions, comments, anything that you want me to repeat before I go on? Okay. So today we're going to just work through a couple of more examples. Ali must have shown you a couple of examples yesterday. I'm going to talk about something which looks like it is a time-constrained LP, but it's really an LP which just looks like the problem that we had with beer and ale. It's just mixing various things to meet a certain requirement. And then I'll talk about some things that are not linear but can be linearized. So those are the two examples that we're going to talk about. And then in the afternoon, I'll apply it to asset pricing. Okay. So what's the story? This example is about something called dedication or cash flow matching. So here's basically the story. There's a municipality that has this obligation. This could be pension plans. Add a few more zeros to this and the numbers become more sensible. A municipality has workers. It's got a pension plan that it needs to finance. There are certain liabilities that it wants to finance. And it's known in advance, which is an assumption typically because people die, new people retire, and so on. So you never know your liabilities in advance. And by the way, this asset liability management problem is really serious. There is a joke that goes around which says that GM is producing cars to pay pension. If you look at the entire liability of pension, it's more than the capitalization of GM. So they are basically producing cars so that they can pay their pension. So pension and asset liability management is a pretty big problem. Typically, the way municipalities go about paying would be by raising money through some kind of a bond. And when they raise too much money, there's a risk that this municipality might go under, which happened in Orange County about 15 years ago or something. So what they want to do is get rid of this liability that they have. They don't want to hold any risk. So they go to an investment bank and say, look, buy bonds for me. I'll pay you money up front today. Buy bonds for me so that their cash flow exactly matches the cash flow that I need. Then I can write this off my books. And in order to do that, what I want is that those bonds be risk-free and non-callable. Non-callable is, so nowadays a lot of bonds that are issued by various companies are callable. A bond, when a company issues a bond, it's a debt. When the company becomes rich, it doesn't want those debts to be there, so it can call the bonds, pay you the money, and say, okay, now I'm not owing you any money. But from the point of view of a municipality that's trying to match liabilities, this feature of callable bonds is a bad thing. Here I was sitting with a portfolio that I thought exactly matched my cash flow, and suddenly this company comes in and calls that bond. So that cash flow is gone from my portfolio, so I have to reassess what happens to my portfolio. So typically when you're trying to do dedication or cash flow matching, you end up not using callable bonds. You don't like them because there is a risk that they could be called. So essentially it eliminates, by exactly matching everything, it eliminates interest rate risk. What the prices of bonds change according to what happens to the interest rate. If you match the cash flows exactly, there is no problem in interest rate. There is another way of matching these cash flows called immunized portfolios, where you match first 2 or 3 moments. In the Excel file that goes with this example, I've shown you how to do the immunized portfolio as well. I will not talk about it right now because in order to do it correctly, you need to know quadratic programming. So we'll come back to this issue of immunized portfolios later on. And they're interesting because this cash flow matching is very expensive. You're exactly matching cash flows. You do not want to take any risk whatsoever. And because you don't want to take any risk, you pay for it. If you're willing to take some risk, you can reduce the cost. And you can reduce it by about 5 to 7%, which is huge. All right, so for our purposes today, all we're going to do is try to match these portfolios. So here's the problem. That was sort of like a background story. Once I tell you the problem, the background story is sort of unimportant. From the modeling perspective, it's all I have to do is, here is a liability stream that somebody tells me. Here are the various bonds that I can buy. And all I want to do is buy these bonds so that they match this liability stream. That's it. So this is sort of basically a problem that we've seen before. You will solve this problem in the bond arbitrage case. In that case, you don't have a liability. All you're trying to do is make sure there's a positive profit today and non-negative cash flows in the future. Here you're saying, I'm willing to pay for it today, but I want the cash flows equal to this. All right? So let's try modeling this. And typically, what are the assumptions that one makes? That you can only hold long positions, meaning that you can only buy these bonds and not sell them in the market. Holding short positions involves risk, and municipalities don't want to hold it. But every time you hold a risk, people compensate you for that, so the cost goes down. So we're going to model this assuming that there are only long positions, and we're also going to model it assuming that any reinvestment that I make, any extra money that I generate in any interval of time, when I reinvest it, I get 0% interest. Why? Because I don't want to expose myself to any interest rate risk. Some of the things that one would want to look at is how to construct the cheapest dedicated portfolio. This is what we're going to talk about right now. What is dedicated? Dedicated comes from the fact that entire cash flow is exactly matched. Portfolio, because it's a collection of bonds. It's a portfolio always refers to when you mix several things to produce a new thing. Here we have individual bonds. We're going to buy different amounts of these individual bonds to try to match a cash flow. What if shorting is allowed? This is not modeled, and this is something that you could play with the Excel spreadsheet and do it for yourself. How much more expensive compared to the immunized portfolio? This is something that's there in the Excel, but I won't tell you exactly how it works, because in order to make it work correctly, you need to know quadratic programming. And what we want to do is, after solving it, try to answer these sensitivity analysis questions. What is the shadow price of the year T constraint? How do you interpret the reduced cost for the bonds, the reduced cost for the excess variables? And is the bond, so basically this is another product. A new product comes in, which price is $103 today. It pays 8% coupon, and its maturity is at 4 years. Whether will you buy that? It's just a repetition of the similar kind of questions that we asked on Tuesday. All right, so let's start modeling it. What kind of variables do I need? So what I want to do is assume these two, assume only long positions. I cannot sell the bonds. I'm going to assume that there's a 0% reinvestment interest, and the question that I want to answer is this one. How to construct the cheapest dedicated portfolio. And so what I want to do is, here are the liabilities for the, how many years was it? 8 years. So liability in year 1, liability in year 2, 3, 4, 5, and so on. And I want to figure out what variables do I need to know. So what I want to do is make it greater than equal to the liability. Well, actually, since I'm trying to minimize cost, I might as well make it equal. And we'll talk about why I can insist on making it equal in a moment. So I just want to take a collection of these bonds and make it equal to those liabilities. And what are those liabilities? They were listed in that table. What variables do I need? What are my decision variables for this problem? Positions on each bond. So let's say xi is amount of bond I. And I takes values 1, 2, up to 10. There are 10 bonds that I can mix, so xi takes values there. Since I only hold non-negative, I immediately have a constraint that xi must be greater than or equal to 0. What else? Do I need any other variables?
Actually, amount of bonds we want to purchase in each year.
Good question. So the question was, what is the amount of bonds that I want to purchase in each year? So that's not what I want to do in a dedicated cash flow. Dedicated cash flow, I want to buy everything right now. So the whole idea behind using this technique, oh no, this is not good. Okay, so does any of you have this typed out? So at least I can use the board. So the basic, if you look at this table, and I'm sorry, this computer's fan has died, so it's going to wake up only for, I'm hoping that in the afternoon class it's going to wake up. But for now we'll have to live with the fact that its computer is not going to be cooperative. Okay. All right, so what in the dedicated portfolio, the total idea behind this is that you buy the bonds today and then you don't do anything with the portfolio. You want to be completely risk-free. You can write it off. It's as if the liabilities no longer exist on your books because you've bought the bonds, they are risk-free, they are not callable, you have exactly matched the cash flow. You can pretend these liabilities did not exist. So I do not want to do any portfolio correction as I go on. But the cost that I pay for making this short-term decision is higher cost. I don't want to take any risk. I'm willing to pay for it. Okay, so given that so these are the only variables necessary to construct the position in the bonds because I buy them only once. Do I need any other variables to model this problem?
Wouldn't you also, it's not about variables, so wouldn't you also need to minimize the cost right now?
Yes, I will try to minimize the cost. So for now, all I'm trying to figure out is what are my decisions, and then I'll write the objective function and the constraints in terms of these decisions. So I'm not writing the optimization problem yet. All I'm saying is that are these variables enough to describe what's happening in this problem? That's about it. So, and then we will have to put down objective, we'll have to put down constraints and so on to solve it. Excess. You can do the excess in two different ways. Typically, we put an equal to sign here and define a new variable called an excess variable. The other possibility is to relax this and make this a greater than equal to sign and not worry about the excess variable. The only reason is that it's possible that in order to match a liability somewhere later on, you produce excess cash flow early on that you're allowed to go through before you don't have to give it up. And so you could put inequality here and then live with it, or define extra variables. So I'm just going to say Z of t is the extra cash or extra cash available in year t. And this t takes values 1, 2, up through 7, let's say. Because anyway, in the 8th year, I want to exactly match, so I won't keep any extra cash. All right, so using these variables, what do I want to do? The objective is simply minimize the cost, whatever is the cost of these bonds, Ci, Xi, I taking values 1 through 10. What about the constraints? What do I do in terms of the constraints?
It's just history.
What did I do with the sheet of paper? Here it is. Whose was it? Somebody. So what constraints do I need to put? This is something that you guys should have done by now, because this is essentially what you've done for your homework.
I get my background is not there.
What?
They're gonna laugh now.
Well, that's me and Ali, and those are you guys. This is what happens on Thursday. Okay, so while this fun stuff is going on in the background, let's try this. Courseworks. Wait. Thank you. Where are we? What? How to pull it down and save it? Okay.
You can just do it on desktop, that's fine.
Okay. Complicated story. Okay. Oh, I don't have. All right, so let's formulate this and then we'll go to the Excel spreadsheet. What did I do with the pen? There it is. Okay, so what constraints do I need on this particular? Let's just try to do it for 1 year, and everything else is pretty much the same. So here is the data. So let's try to see what happens in year 1, and then maybe year 1 and 2, and then we'll be okay with the rest of them. What is the cash flow in, what is the constraint that I need to put on year 1? And the CIs here are basically the cost of the bonds. So what is the cash that I'm getting out of bond 1 in year 1?
The amount, the bond for the first one and the coupon.
So it's 105 times x1. What about x2 and so on? You just get the coupon payment. So it's plus 3.5 x2 plus, and so these are annual coupons. If they were semi-annual, you'll have to cut them by half and so on, plus blah, blah, blah. And the 10th bond would give me 7 times x10 minus z1 must be equal to L1. So what happens, so question back there? Any questions? So the coupon payment is paid on the face value. The face value of all of these bonds is 100. So every coupon, and I'm assuming here that the coupons are paid annually. So the coupon on bond 2, which has a maturity in year 2, is 100 times 3.5%, which is 3.5. Okay. What about in year 2? There is nothing coming out of bond 1 because it already matured. Bond 2 matures, so you get 103.5 x2 plus 105 x3 plus so on plus 7 x10 plus z1 minus z2. And the fact that I'm assuming 0% interest gets interpreted in the fact that whatever I put into my excess cash in year 1, the same amount shows up in year 2. And Z2 is the amount of money that I put away in year 2. Right? So every rest of them is exactly the same. You just try to figure out which are the bonds that are maturing, in which year are they maturing, add them up, put down the relevant. So here it will be just simply plus Z2 minus Z3 and so on. Question?
What's the benefit of using the Z variable?
The benefit of using the Z variable. Question is, why do we care about the Z variable? You can do it in 2 ways. One way you can do it is to make this an inequality. But whatever x, so what might happen, there are 2 things that one thing is you can make it an inequality and pretend that this variable doesn't exist. But one thing that you have to make sure is that whatever is the difference between these 2 is carried over. Because it's possible that the bonds are in such a way that there is excess cash that is generated in one particular year. The minimum cost portfolio of bonds is such that it creates an excess cash in 1 year that you want to carry over to the next year. You cannot insist. Question?
What if we can reinvest excess cash? What if we can reinvest?
When you can reinvest, what will happen? You tell me the answer. What happens? If you could reinvest the excess cash,
we can reduce the coming liability in the future.
Yes. So this is an assumption that has been made in this particular case. The reason when you're doing this dedication, people typically do not want to assume that there is a reinvestment rate is because you're making a 10-year horizon decision, or 8-year in this case, and interest rates might change. So something that you think is completely provided for right now, you may not be able to provide for it later on. Instead, what you would want to do is assume that the interest rate is given by some uncertainty and try to correct for it using some quadratic programming. In this particular case, even if there was an interest rate given, you can still account for that without the Z variables. All you have to do is take the difference and multiply it by 1 plus R times and add it to the next thing. The only relevant thing that, the reason this question is relevant is because what might happen that you might make money using interest, or you're forced to put cash away because of the cash flow that happened. So you have to allow for the possibility that some of these equalities are in fact inequalities. You can either put it by explicitly putting an inequality or by putting a variable which keeps up the slack. It's more convenient to put in the slack variable. Oh, come on. Today is not a good day. Power save mode. Another reason is something that I mentioned even last time, is from looking forward, one might want to ask some scenario type questions as to whether it makes sense for me to borrow money in this particular period or not. And in order to do that, I want to create its reduced cost in my sensitivity report. And one way to get that reduced cost is to have a variable. Otherwise, you don't get it. width. Good. Okay, thanks. Go back there. Any other questions on the modeling? While we are waiting for this to wake up and give me my Excel file. All right. So here's the Excel file, and all it's doing is setting up this particular problem that we just said. So B1, B2, B3 up to B10 are the 10 bonds. Z1 up through Z7 are the excess variables that I could keep. And each of them is an equality constraint. And if you solve it to optimality, you end up getting a cost of $93,896 to match up all of these liabilities. Now, if you did the immunized portfolio, which I didn't talk about how to formulate, you end up getting the cost to be $57,812 in this particular case. So you're almost paying, about a third more, maybe, to buy a dedicated portfolio than to buy an immunized portfolio. So immunized portfolios are good. People don't want to pay a third more simply to remove risk which may not even exist. The whole idea behind immunization is that there is some amount of interest rate risk that you don't want to incur. So let's go back to our dedicated portfolio and try to answer the questions that we put up. So before even answering, let's see what do we need to answer these questions. So all of these things, the way it's been set up, are going to be answered by sensitivity analysis. First two are the first one is going to be done by looking at dual prices or the shadow price. The second two are going to be done by the reduced cost. And the last one, again, is just the trick of trying to figure out what happens to, we'll just try to see what that one does. So let's go back and solve this thing. So here is the sensitivity report for this particular problem. And let's try to answer what happens. Bless you. So here are the questions that we want to answer, and then we'll go back to the report and see what those answers are. First, I want to interpret shadow price of the year T constraint, or let's say year 4 constraint. It doesn't really matter. It's the same idea, so let's just put a concrete number. The second thing I want to talk about is what is interpret the reduced cost. Of the bond variables as well as the excess variables. The next one is we want to talk about whether is the bond, which is characterized by 103, 8, and year 4, interesting. Meaning, would it reduce my cost? All right, so here is the report. Let's try to figure out from there what do we do. So what is the interpretation of this guy? The shadow price of the year 4 constraint. What does it mean physically? So the dual price for the year 4 constraint here is 0.83576, so 0.84. So the dual variable here is 0.84. What does it mean? From an economic point of view, what would that variable mean? So if I increase the liability in year 4 by $1, what will be its cost for me today?
83 cents.
83 cents. What does it mean now? Physically, what does this 83 cent mean? Assuming that the 10 bonds that I considered, or was it, yeah, it was 10 bonds. Assuming that the 10 bonds that I considered were the only risk-free bonds that were available in the market. I considered all possible bonds that they were there. Risk-free, non-callable bonds that were there in the market, there were only 10 of those. Then what does this number 83 mean? The present value, the risk-free present value of $1 in year 4 today. So in this particular case, if I look at the dual variables corresponding to all of these constraints, and I construct, so if I wanted to, what kind of an interest rate does this 0.84 imply for 4 years? How would I compute that? So I set this equal to what? I mean, of course, if you're good at computing this thing, very good. 1 over 1 plus R, let's call it 4, meaning it's an interest rate that refers to something that is achievable only in year 4, raised to the power 4. And you solve for this, you get R4, whatever R4 is. So I could do this for year 1, year 2, year 3, 4, 5, up to 8. What do you end up getting out of that? And this is something that only people who had seen finance would, the term structure. So the dual variables in this particular case, if indeed the bonds that I considered were all possible risk-free bonds, gives you the term structure. If you don't understand what a term structure is, this is a term that I'm unwilling to explain right now. It just will take me too much time. You will see this in FE1. But for now, interpreting it just one variable at a time makes sense. And together, they define the term structure of interest rates. So a lot of what is happening, so if I get to it this afternoon, you will see that the dual variables in another context give you some other kinds of prices. So this notion that the dual values are actually a price is really there all over the place. So the term structure is the price of $1 in the future today. Question?
What if there is a discrepancy between the implied term structure and the actual prevailing term structure in the market?
What does that mean?
I mean, if suppose your implied value is different from the one that we observe in the market.
So the question is, what will happen if the implied value by our term structures is different from what is implied in the market? There is an arbitrage opportunity, one thing. Now let's interpret the same thing in another way. If it turns out that the implied term structure is exactly equal to the one in the market, what will it tell me about the immunized portfolio versus the dedicated portfolio? Exactly the same. If the interest rates in the market, if the dual variables that you get out of this give you exactly the same term structure as exists in the market right now, then if you're immunizing a portfolio versus dedicating a portfolio, you won't get a difference. The difference comes in because there's a mismatch. Typically, this particular interpretation, while very cute, is utterly useless, because when you're trying to solve these problems, you would never want to take all possible bonds. And so if you're not taking all possible bonds into account, then the dual variables do not necessarily have to be the interest rate. Question?
Relating to the immunized portfolio versus this portfolio, I was just wondering if the immunized portfolio is primarily a first moment or a second moment portfolio, is that when it would match? Because an immunized portfolio could have a level of...
Right. Good question. So the typically people match 2 moments.
Yeah, 2 moments.
That's it. So in general, more than that, you'll probably want to go something like VAR kind of portfolios. You won't do immunized. So when you say immunized, it has this meaning.
I
Now,
was just wondering what kind of a spanning set would, I mean, if the entire bonds that you've taken right now,
yes,
and you've matched the cash flows, exactly.
yes,
Then when comparing it with the immunized portfolios, you have the 2 moments.
yes.
I mean, you made the comment that it would exactly, I mean,
The costs would be the same. The portfolios need not be the same.
or could we rather reframe that as the immunization level increases, the cost of immunization would tend towards the cost achieved through a dedicated portfolio?
I don't know the answer to that question. So the question was that as the immunization level increases, would it go to the cost of the... so the thing is that the reason I'm hesitating with that is in a multidimensional optimization problem, if you match higher and higher moments, it doesn't necessarily converge to the problem where the values are exactly matched. If the problem was one-dimensional, then what you're saying is absolutely true. It will match as you start matching higher and higher moments. But since here it's a multi-dimensional problem in the sense that there are a number of independent variables that you can control, I cannot say for sure that it's going to match. It may be the case in this particular application it matches, but in general you cannot make that statement. But it may very well be the case that for this bond problem it matches, and I don't know the answer. I don't know whether it will.
Can you explain why the shadow price relates to the interest rate that way?
This way. Okay, so what happens is, so it should be pretty clear to you that 84 cents is the value of $1 in year 4, right? So right now the dual variable for year 4 is 83 cents. And therefore if I increase my liability in year 4 by $1, I pay 83 cents today. So the net present value of $1 in year 4 is equal to 83 cents today. So this basically is doing a net present value calculation. In year 4 you get $1, so you can do the net present value, you end up getting this. So you compute for R, you get the interest rate. Okay? Any other questions about this interpretation before we go on? So those of you who don't know term structure of interest rates and things of that sort, the one thing that I do want you to remember is that the relationship between the dual price and interest rate. And it implies an interest rate because it gives you the value of $1 in the future. What it implies in terms of the term structure, this to the right-hand side of this line is not something that you're responsible for. But on the left-hand side, you need to know how we ended up computing that quantity. All right. So let's look at the reduced cost of the bonds and the excess variable. Let's pick a particular bond. Bond B3. Its reduced cost is 0. What would it mean in terms of the optimum solution? Suppose all the other columns were absent from this table. Only column you could see was the reduced cost column. If you found that its reduced cost is 0, what would it imply to you in terms of the portfolio that you constructed?
It is part of it.
It is part of a portfolio. So if the reduced cost is 0, it means it's a basic variable, which means that it's part of the optimum solution that you have created. This is just a sort of, what it means is that nobody has to give you any more incentive for you to buy this bond. You've already bought it, you're happy keeping it. So if that is the interpretation, what does this mean? What does this 0.83 over there mean? So for bond B2, I have a reduced cost of 83. Yeah?
Does that mean if you increase your position in bond 2 by 1, it's going to increase the objective function by 83 cents?
Right. One thing is that. The other way is, so one way of interpreting it as if you insist on buying bond 2, it's going to increase your objective value by 83 cents. And since you're trying to minimize the objective value, you don't want to do that. Another way of doing it, another way of interpreting the same thing is if the price of bond 2 was 83 cents cheaper, you might consider putting it into your portfolio. Question?
But that border of the allowed will decrease. So we
Which?
thought, this reduced cost, that is also something.
So that's why I said you might be. You can't be sure. But at this present moment, you're absolutely sure that you won't be interested. What about this guy over here? B7, 8.78. If you saw data like this these bonds were actually cooked up and not real bonds, but suppose you actually really picked up the bond data and solved this dedicated cash flow problem, looked at the sensitivity analysis, and you ended up getting a number 8.78 here. What would be your first reaction?
Shouldn't buy that one.
For sure, you wouldn't buy the bond. Anything else? There's an arbitrage opportunity sitting there because it's just too highly priced. It appears that that bond, nobody's going to really look at what's happening. So you might want to short it and buy something else. Another possibility, which is probably more likely than any of these other possibilities, is that the data was inputted wrong. Typically, I mean, this is on $100. If you're saying somebody is mispricing it by $8, it's a huge amount. I would first guess that maybe the data is wrong. Yes.
Whenever you have non-zero reduced costs, that
Yes.
automatically mean they're not in the basis.
Yes. Non-zero automatically means they are not in the basic. Zero doesn't necessarily mean that they are in the basis, because it could be that it's a non-degenerate problem. What else? So the reduced costs basically tell you what compensation should you be given in order to include a particular variable into your portfolio, or what is the cost of including that portfolio. So it increases by 83 cents. So if somebody gives you a discount of 83 cents, you will consider putting it into it. What about these guys? Can we interpret these reduced costs in some way of the excess variables? Does it have any interpretation? So all of them are positive, which basically means what? Which basically means that you exactly funded your liabilities without putting any excess cash away.
This also corresponds to say the prospective interest that you're looking at in order to sort of generate or come up with such a portfolio that gives you extra cash at the end of the day.
Right. So that's absolutely right. These numbers should somehow be interpreted as the minimum interest rate that you should be given in order for you to put away money at a particular year. But not exactly. It's not as clean as the relationship of the shadow price. But that's something that you think about, and if you don't get it, I'll explain it again. But these should, somehow this should be interpreted as the value of putting away, the minimum value that you should be given to put away $1 in year one. But the reason it's not exact is because we're saying that any dollar that I put away in year one reappears in year two. So it's sort of a little bit misleading as to what does that number mean. But it's something related to the value of the dollar, but not exactly. But you can interpret it. All right.
So,
Yes.
for V2,
Yes.
the reduced cost is 0.83.
Yes.
Does it mean that we have to invest one bond? If we buy one bond, then the cost will increase by this much?
Yes. Whatever is the unit, one bond.
One bond.
Yeah. I mean, one bond, 100 bonds will be 83 times this. So here the xi's, the variables are gone. The xi's were number of bonds, and therefore it basically means whatever unit that you use for the variables, that's the unit that you have to multiply in order to get the value. But, so I didn't quite explain it completely. So the only intuitive idea that I can give you, and the rest of it that you have to fill it up yourself, is the notion that we have about reduced cost is that it is the minimum compensation somebody has to give you for you to be interested in doing that activity. Somebody has to pay you 83 cents more, which means its cost has to drop by 83 cents for you to consider buying B2. You may still not do it, but for you to even consider it, that has to be done. So what does Z1 mean? Z1 is the decision to put away money from period 1 to period 2. Question?
For all the non-basic variables, the reduced cost happens to be same as the allowable decrease. Will that always be so? Or is
No, this is just a chance. It's just a chance. It will never be, it need not always be the same. The reason it becomes this is because of the particular structure that you have here, a variable going out, coming in, going out, coming in. So it sort of has this flow interpretation. That's why you end up getting this kind of structure, but not in general. Okay. So going back to your question, if So Z1, what I'm saying is that this activity Z1 is putting away $1 in time 1 in order to use that dollar in time 2. That's the activity that is associated with Z1. And what this reduced cost says is that somebody has to give me, whatever, 5 cents in order for me to consider putting away the dollar for 1 year, starting it from year 1 to year 2. Similarly, somebody has to give me 3 cents in order to put away $1 in year 5 for it to reappear in year 6. Now, that doesn't, I mean, it has an interpretation in terms of interest rates, but not exactly the same as this one. Similar, but not exactly. So, the general rule that I would tell you about reduced cost is that think of it as the value of doing that activity. Yes?
In this case, where the reduced cost is equal to the allowable decrease,
Yes.
can you strongly state that if the reduced cost is reduced by exactly that amount, it would be in the basis of the new solution? Because the allowable decrease is that it's going to calculate a new optimal solution. The only thing that's changed is that variable. So wouldn't it have to be in the basis of the new solution?
I would probably argue that that is the case, but I can't say for sure right now. So let me think about it and I'll get back to you. I suspect that your answer is that so the comment made was that since the interval is exactly equal to the reduced cost and nothing else changes, and therefore this variable should enter the basis. The answer is I don't know yet, but I can look it up and I'll tell you what the answer is. Okay, now let's talk about this one. How would we solve this problem? Is the bond, which has a price of $103 today, it pays an $8 coupon and has a 4-year maturity, interesting. Would I buy this bond? How would I solve this problem? Using the data, of course I can put it right into the LP and it will solve it for me, but using the sensitivity analysis data, can I answer this question? This is very similar to what we've done before. This is introducing a new product. The old mix of products had 10 bonds. I created this sensitivity analysis using those 10 bonds. Now I have introduced an 11th bond. And I'm asking you whether this 11th bond would make a difference. How would I formulate this problem? Or what would I do about this? Any ideas on? So the way these problems are solved is, again, you assume that the problem is non-degenerate. So it's a nice little corner, and therefore if you perturb things slightly, nothing's going to happen. If it happens, well, our guess is wrong. But let's say, and then let's say we just buy this bond, a delta amount of this bond. I can only hold long positions. So buy delta amount. So the cost of this is going to be 103 times delta. And what is, so basically I have to do a cost-benefit analysis. The cost of buying this delta amount of bond is 103 times delta straight out. What is the benefit of buying this bond? What does it do to me? How does it change my liabilities? So the vector change is going to be whatever it was, 8 delta, 8 delta, 8 delta, 108 delta, and zeros. So this is year 1, 2, 3, 4, and zeros from 5 through 8. So let's actually put 3 zeros in. There we go. So that is the change in the liability that happens. What is the value of this change to me? What does it change in terms of my cost? What is the benefit of having reduced my liability by this amount? How would I compute its value? The shadow prices. You multiply it by the corresponding shadow prices. So if I look at the shadow price vector U as a vector, then I'm just taking this inner product. By a vector, I mean just stack these 8 guys into a vector. This is an 8-dimensional vector. You compute the inner product of it, meaning take the first component of this multiplied by the first component here, the second to the second, and so on, and add them up. So that will be the cost, that is the benefit. So it's going to be U transpose times 888,108,0,0,0 times delta. So interesting, and let's just call this vector delta L vector. So this bond is interesting if 103 is less than delta L times, or U prime times delta L. If the cost is less than the benefit, you buy it. If the cost is greater than the benefit, you don't buy it. Are these interpretations clear to everyone? So, just to reiterate everything until it gets completely boring. So my intent is that it should be such that the moment such questions come, you should immediately know how to answer them without even thinking too much about it. So when you change the right-hand side, the shadow price tells you how much do you pay for it. When you look at the reduced cost vector, it's telling you how much does somebody have to compensate you in order to take on that activity. So 0 means that you're already doing that activity. Nobody has to compensate you anything, so it means it's in the basis. Typically. There is a case that if it's a 0, it may not be in the basic. But that's an unusual enough situation that we won't worry too much about it. If it's non-zero, it means somebody has to compensate you something in order to put it into the basis, and that's what the reduced cost vector tells you. Okay. That's pretty much what I wanted to say about this example. Any other questions before I go on to the next thing? All right. So the next story that we're going to talk about has got really nothing to do with it. We're going to make a change and actually go to the next lecture. Where is desktop? Oh, not good. I have to download that lecture. So in this case, we're going to start looking at problems that don't look linear but can be linearized. And they show up in many situations. The first one we're going to look at is in a data fitting model. So here's basically the story in this data fitting model. You've been given some vector of points. So there are m points that are given. And at each of these points, each of these vector points, which are described by, say, a vector a1, you're given a scalar value b1. This point is the vector a2, and it's got a scalar value b2. You can think of this as if in the homework that you're submitting today, you have to find out what is the volatility that fits everything. So there are certain strike price, a certain stock price, and a certain time horizon that's been given to you. That's your vector A1. B1 is the option price at that point, and you are trying to see whether you can predict the option price looking at whatever is the independent variable. So this model here is a much simpler model than that. We're going to look at a linearizable model. So I'm going to pretend that all of this data has a prediction of this form. The scalar value can be predicted by taking a vector beta times the vector value. So I'm going to say that the value here, B1, has to be close to beta transpose times A1. So beta is a vector, A is a vector, and this is what my guess is of how this data can be summarized. Okay? And I'm going to try to compute that by solving this problem. I want to minimize the maximum possible error that I see in the data. All right? This particular problem is not a linear program, because this function here is not a linear function. It's a maximum of some absolute values. Even if this maximum were not there, an absolute value by itself is not a linear function. A linear function just looks like A transpose times another vector. Yes?
Can you explain the formulation? As in, you have the vector and then you have a point next to
A value.
value.
Yeah. So think of here's the value. You're given a strike price. You're given a strike price. You're given a time to expiration. You're given the current price of the option, of the underlying asset. And for all of these three vectors, you're given the option price. Let's call it little p. So this three-dimensional vector, I'll call it A, and this guy, I'll call it B. So it's a vector that describes the phenomenon. In this case, those are the three numbers that describe the phenomenon. And what is the phenomenon? There is an option, and it has a price. That's the scalar value that's sitting there. Typically, as is the case in the homework problem, there is a nonlinear function that predicts the value of B given A. Here I'm saying that I'm going to look at a linear function predicting the value B given A. So instead of trying to fit a nonlinear function to that problem, I'm trying to fit a linear function. In the particular example that you will do in the homework, you're going to try to minimize the sum of errors. Here, we'll go to that one too, and that'll just be an exercise in a moment of how to do the sum of absolute value errors. But for now, let's say I want to minimize the maximum of the absolute value errors. That function over there is not a linear program because the function in there is not the absolute value function is not linear. When you take a maximum of certain things, it's not linear. And the question is, can I still solve that as a linear program? Ali, did you end up doing this?
I just talked about how to change the max part.
Okay. All right. So since we know how to change the max part, let's start with that. How would I reformulate this problem to start looking more like a linear program? Well, I don't want to approximate anything. My claim is that this can be solved exactly.
Decomposing into positive and negative parts.
We can form it into m different constraints.
So decompose what into positive and negative part for each of these?
The max function.
The max function doesn't have positive or negative part, right?
The absolute value.
The absolute value function. So let's keep that in the background. We'll come to that in a moment, but that's not the solution I want right now. So the solution suggested was decompose absolute value into A plus plus A minus. And for those of you who don't know that, I'll get to it in a moment. But I want to find a simpler way. So typically when you do this decomposition technique, you increase too many variables. You put too many variables that are necessary. So let's try to see if there is some way of doing this problem without introducing too many variables. Doesn't work all the time, but in this particular case it will work. And then we'll show you the decomposition technique as well. So let's first try to do it step by step. Let's not worry about the absolute value for now. Let's just think as if there was a linear function sitting here. And it was just minimizing the maximum of a linear function. What do I do in that case? Suppose the problem was just simply this. Minimize the max of 1 less than I less than m. And if that confuses you, let's just put the max of this. B1 minus beta transpose A1, B2 minus beta transpose A2, B3 minus beta transpose A3. Suppose this was the problem. This absolute value is another annoyance that I have to take care of. But for now, let's just talk about this. How do I solve this problem? Yeah.
We introduce a new variable.
We introduce a new variable, and what do we do with that variable?
And we say that y, we introduce three new constraints.
Yeah.
We say that y must be superior to v1 minus v transpose x1.
Right?
And the structural others.
And the other two.
And the problem is now to minimize the y.
Minimize the y. Okay. So the suggestion is, the way to think about it, is to look at this max and set that max equal to some variable y. And this is not, so let's pretend that this max is equal to some variable y. Then we know that since it's a maximum of these three quantities, we know that what we want to do, what this implies, that B1 minus beta transpose A1 is less than equal to y, B2 minus beta transpose A2 is less than equal to y, B3 minus beta transpose A3 is less than equal to y. And I want to minimize the value of y because that's what the outer problem told me. So I want to put a minimization over this. So minimize y such that these constraints hold. So then these two problems are exactly the same. All right? Okay. Now let's go back to the problem that we really wanted to solve with these annoying absolute values. This is the problem that we wanted to solve. Now does it tell you how to make it into a linear program? Okay. When I put absolute values there, this is the same thing as saying putting absolute values here, right? All I did in order to construct this LP, or which was an LP before, was to say that I set y equal to the maximum of the three quantities that sat inside that curly brackets. That implied that y must be greater than each of them, and I'm trying to minimize y, so that gave me the optimization problem. Now, let's try to do the same thing. Instead of having a linear function sitting there, I now have this absolute value guy sitting there, but this analysis is still true, right? All I'm saying is I'm minimizing y such that y is greater than these absolute values, so far I'm good. Now the problem is that this is not a linear constraint. An absolute value, some y greater than equal to an absolute value is not a linear constraint. How do I get rid of that and make it into a linear constraint?
So we introduce two variables.
Don't want to introduce any variables. Yes?
You can just write it as B1 minus beta transpose A1 is less than y, and B1 minus beta transpose A1 is greater than or equal to negative y.
Yeah.
Each of the constraints.
For each of the constraints. So here's what is happening in the background. What is happening is that if I write some two variables, u is less than equal to, the absolute value of u is less than equal to v. What is the absolute value of u equal to? How can you write it? This quantity, the absolute value of u, is in fact equal to this, the maximum of u and minus u. That's exactly equal to the absolute value of u. If u is a positive number, then this maximization picks out this term. If u is a negative number, then this maximization picks out the other term. If u is 0, it doesn't really matter. Both of them are equal. So absolute value of u is equal to this maximization. So this constraint, less than equal to v, this constraint is the same thing as saying u is less than equal to v and minus u is less than equal to v. So let's try it here. What am I doing here? I'm taking the stuff that's inside the absolute value, taking itself and setting it less than equal to the right hand side, taking the negative of what's there inside the absolute value and putting that less than equal to v. So each of these constraint is the same as the constraint b1 minus beta transpose a1 is less than equal to y, and b1 minus of b1 minus beta transpose a1 is less than equal to y. This is exactly what was suggested, except that I wanted to show you how it came from looking at a maximum of two functions. This can be equivalently said as b1 minus beta transpose y is greater than equal to minus y. Yeah?
How would you do it if instead of less than sign, you had greater than sign?
Very good question. I was going to come to it in a moment.
That's the same thing. Then you just have it like greater than y and less than negative y.
Let's just finish this story. It turns out that it's a little bit more complicated than that. Something goes wrong there, and we'll discuss it in a moment. So at the end of the day, let's finish this story and then I'll answer that question. So at the end of the day, I end up getting a formulation which looks like b1 minus beta transpose a1 is less than equal to y, minus b1 plus beta transpose a1 is less than equal to y, and so on. B2 minus beta transpose A2 is less than equal to Y minus B2 plus beta transpose A2 is less than equal to Y, and blah, blah, blah. Okay, now returning to the question that was asked just now, let's do, the same question actually comes up in a different way. Let's try to solve another optimization problem, and let's see what happens then. Suppose this was the problem. I want to minimize the minimum of these quantities. What happens then? Can I reformulate that problem somehow? It'll show up, the question that was asked will show up if I try to reformulate that problem. Or actually, let's turn it over. Yeah, actually, let's keep a minimum here. Let's not put a max there. Then some nice things will happen. So if I'm trying to do that, what do I have to do here? Now, very easily, what I'm going to do is reformulate the problem into this. B minus beta transpose A1 is greater than or equal to Y. B2 minus beta transpose A2 is greater than or equal to Y, and the next constraints, whatever they are. So this is what the reformulation would be. Now, can I linearize this? So if the absolute value of a quantity is greater than Y, let's go back to our simple problem. I'm claiming this is what the constraint looks like. So this constraint means that the maximum of U and minus U is greater than or equal to V. Yeah? They're not equal, but I'm just pretending that I'm going to solve that problem using this problem. So the question is, are these two problems equal? I should erase this thing. They are formally, I'm trying to solve this problem, I'm pretending that I can solve it trying to do that. They are not equal, and they are not equal because of this problem that happens. So this is a constraint that I'm really trying to think. I mean, those things are just disguising, there are some vectors there and whatnot, but really what I'm worried about is this. Can I linearize this? Yes?
You did in the last page, right?
Can you?
Weren't you?
Well, so those of you who think that this can be linearized, let's try it. What is the linear solution? Forget about the variables. It doesn't really matter, right? Ignore this absolute value for now. I just gave you this constraint. Maximum of U and minus U has to be greater than or equal to V. There's no point in producing new variables at this point, right? So how do you represent this constraint? What does this mean? So think about the difference between these two statements. Max of U and minus U is less than or equal to V versus max of U and minus U is greater than or equal to V. Is there something different, fundamentally different between these two constraints?
The second one you have a closed interval, but probably in the other one you don't.
What does that mean? Well, feasible region's already there. It just says it's disconnected. It's like one is over there and one is over there. Yeah?
It's like an OR statement versus an AND statement. The first one's saying U has to be greater than or equal to V, or negative U has to be greater than.
Exactly.
Less than or equal to V. Right?
Or whichever way. I want to think everything in terms of greater than or equal to right now. So this implies that either U has to be greater than or equal to V, or minus U has to be greater than or equal to V, whereas this constraint means that U has to be less than or equal to V, and U has to be minus U has to be less than or equal to V. That's what, if a max is less than a quantity, this is what it means. Both of them have to hold. If a max is greater than a quantity, it means only one of them has to hold. In linear programs, we can never do this.
I have a question.
Yeah?
So can we transform this OR into two optimization
Sure.
problems, and then the combination of the three will turn out to be 8 problems?
Yes.
Solve 8 problems. Yeah.
But you can solve 8 problems. However, there is a better way of doing it. Solving 8 problems, I mean, typically when you want to solve these, when you try to do these data mining problems, you'll have something like 100 data points. 2 to the 100, 1024, you could still, no, 2 to the 10 is 1034. 2 to the 100 is a bit on the higher side. You might want to avoid it. But yes, conceptually, you can do it. And what you're implicitly doing there is enumerating all possible cases. When you're saying that you want to solve 2 to the n problems, you're enumerating all possible cases. Usually there are better ways than that. But for now, all I want you to remember is in linear programs, we can never put this kind of constraint because we can only put all constraints in there. We can say it must satisfy that constraint and the next one and the next one and the next one. We can never say it must satisfy a subset of these constraints. That's what this is saying. Either it satisfies this one or it satisfies that one. It doesn't have to satisfy both. And this, therefore, will not work. Okay. So what time do I have? Let's see. So let's try to do the same thing now and use this decomposition idea, which is something that's also very interesting. So in order to use that idea, let's try a different optimization problem. Suppose I want to minimize the sum of I going from 1 through m of absolute value of bi minus ai transpose beta. So this problem is trying to minimize the maximum error. Here I'm trying to minimize the sum of the errors. And of course I can do it. How do I do this? By the trick that we have so far. How would I solve this problem? By putting an upper bound idea. Let's not go to the decomposition. Let's just try to see. So far what we have done in trying to solve these absolute value type problems is to introduce a new variable which bounds the quantity from above. And then I use the fact that an absolute value of u less than or equal to v basically means two linear constraints. So the basic trick is anytime I see an absolute value sitting there, I upper bound that by a certain variable and then replace this by two constraints. So if I wanted to do that trick over here, what would I do? You introduce m variables because I cannot just upper bound the sum and do the constraint. So I introduce m variables, each of which upper bounds each of these quantities. I put the sum of those yi sitting there, and then I have two constraints for all of them. So that's one way of doing it. Another way of doing it is through that idea of decomposition. And what you do in the decomposition idea is to have this thing, that if you have a number x, and you can always decompose this number x into its positive part minus its negative part. And what is the definition of x plus? X plus is equal to the max of x and 0. So if x is positive, x plus is equal to x. If x is negative, x plus is 0. X minus is defined the same way. It's the max of minus x and 0. So if x is negative, you end up getting that x minus is positive. If x is positive, you end up getting that x minus is 0. So the way to remember this is x plus tells you the positive part. If it's positive, it just gives you the value. If it's negative, it gives you 0. X minus gives you the negative part. If it's negative, it gives you its negative part. If it's positive, it gives back you 0. So you can always write x into this form, x plus minus x minus. And the absolute value of x is what? In terms of these variables? X plus plus x minus. And the other thing we also know that each of these variables is non-negative. The way they are defined, x plus and x minus are non-negative variables. So one way of solving these problems is every time you see an absolute value, put in two variables. Take the addition of the two variables, set it equal to the absolute value. Take the difference of the two variables and set it equal to the argument that's sitting inside the absolute value. So for each of these, I'm going to put in two variables. I'm going to set bi minus ai transpose beta equal to ui minus vi. So I'm going to pretend that ui is the positive part of this quantity, vi is the negative part of that quantity, and I'm going to set that bi minus ai transpose beta is equal to ui plus vi, and I'm going to insist that ui and vi are both non-negative. So I introduce two variables for every absolute value, and you end up getting this. So now the optimization problem becomes, let's not write it down below. So whenever there is an absolute value, I put in those added variables. So I going from 1 through m, ui plus vi, such that now I have to tell you that the quantity that was sitting up there is actually related to ui and vi. So bi minus ai transpose beta is equal to ui minus vi for I taking values 1, 2, up through m. ui and vi are both greater than or equal to 0 for I taking values 1, 2, up through m. So that's how I make it into a linear program. Okay, so these are two different tricks. They are, if you think about it, they are basically equivalent. They are, it's just algebraic manipulations. If you get it in this form, you can always reduce it to the optimization problem that I would have gotten by taking upper bounds. If you get upper bounds, you can always transform it into this one. So if you took the upper bounds, you would have gotten this optimization problem. Minimize sum of yi, I taking values 1 through m, such that ai or bi minus ai transpose beta is less than or equal to y, and minus bi plus ai transpose beta is less than or equal to yi. I taking values 1 through up through m. And I don't have to impose the constraint that yi is non-negative, because yi is being lower bounded by an absolute value. So yi by definition would be non-negative, right? And I leave it to you to figure out that, in fact, if I give you an LP that looks like this, you can rewrite it into an LP that looks like this, and vice versa. You can just eliminate some variables and you can get from there to here, and eliminate some other variables, or add some variables, and you go from here to there. It's
why is it less than or equal to instead of equal to yi?
You don't know whether they are equal to, because only one of these will be equal. Either the positive part will be equal to yi, or the negative part will be equal to yi. So you cannot make it equal to, because then it will basically say that all of them have to be 0. Question?
Which is it easier to solve?
I personally favor this one. I don't like too many variables. So in terms of trying to solve the problem, this one starts putting in lots of equalities. Equality constraints are okay for simplex. But if you've got a large problem, typically the solver is going to solve it using interior point methods, which we won't talk about in class. But interior point methods don't like equalities that much. So if you avoid equalities, it's good. But unless you're getting into, at least like tens of thousands or hundreds of thousands of variables where this is happening, it doesn't matter, whichever you're comfortable with. I personally like this one because I don't have to introduce new variables, but classically this is what is taught in LP classes, because that's what makes writing the problem very, very much simpler. People can automatically write it. If you were an OR student to begin with, this is what you would have seen. If you were not coming from OR background, this is what you would have seen. So there's a bias of where you came from. All right? So we'll see you again in the afternoon.
Do you think also